Okay, so welcome back. We are continuing with that ground back CPW line. So let's come back here. So in ground back CPW line, we have one additional ground plane. If I now plot the electric field inside the structure, you see we have the CPW basic CPW line, and the central part we can consider it looks like a microstrip line, right? Because we have now this additional ground plane. So in this case, what we see practically, we have the CPW mode. So electric field parallel to the dielectric air interface. In addition to that, we have microstrip line mode, which will be perpendicular to this bottom ground. So you can see from the right hand side figure, we have CPW mode inside the slot as well as we have microstrip line mode, both together, and these two modes have almost similar velocities. So the dispersion effect usually we neglect it, but we may have higher order modes, and that is associated with different velocities, phase velocities. So if somehow those higher order modes are excited, then phase velocities will be different and will be facing dispersion effect. So to avoid that, what we do, so the limiting frequency, we define one limiting frequency which is Fg here. It is determined by the point where the phase constant of the CPW mode and the first lateral higher order mode, they intersect. So this is the next higher order mode, and approximately it can be given as Fg equal to 2 by W total square root of twice mu naught epsilon naught into epsilon r minus 1. So it depends on the total width. What is W total? This is from leftmost point to rightmost point. So twice Wg plus W plus twice S, and it also depends on epsilon r. So in this case, you see we have one problem. What problem it is? The problem is that surface wave generation. What type of surface wave we may have here? TE wave, already we discussed. Now since we have microstrip line mode, we may have TM wave as well. Not only that, if we have a thicker Wg, too wide, in that case we may have also parallel plate mode. So all these three surface wave can be generated, and the line will be very lossy. We can avoid this surface wave to some extent by using periodic vias. So what we do, let me draw the top view of this modified ground back CPW line. So this is the signal line, let's say, and I am drawing the ground line here. So it shows the top view. So this is my signal line, its width I am showing by W, and this is the ground plane, ground line, top ground line, the width is given as Wg, and then we drill periodic vias which connect this top ground to bottom ground. And you see what is the advantage of this periodic via, which are metallic via. It will suppress TM mode as well as parallel plate modes. So the resultant structure you can see here, these red lines, it shows those periodic metallic vias, those connects this top and bottom ground plane, and we can avoid leakage to surface wave in that way to some extent. Now in semiconductor fabrication procedure, it is not easy to create periodic vias. So in those cases, mostly people will use either a conventional CPW line without any ground backing, or a ground back CPW line without periodic vias. In that case, we have to follow some thumb rules if we do not use that periodic vias to keep surface wave mode generation minimum, and those rules are listed here. Keep the ground width Wg less than lambda d by 8. So, this is to keep radiation loss and dispersion small, and keep the total width W total less than lambda d by 4 to avoid coupling to parasitic mode, other higher order modes. So, lambda d, this is the guided wavelength in ground backed CPW lines. Now, to give you some ideas about loss variation and beta variation. So, once we have the variation of effective epsilon, from that we can estimate what is the variation of beta versus frequencies. So, we are considering a silicon substrate semiconductor technology. The thickness is 411 micrometer high resistivity silicon, rho more than 2500 ohm centimeter. So, you remember what is high resistivity silicon? It is more pure silicon. So, doping concentration is negligibly small, and epsilon r, it is 11.9, and the metal we are using gold of thickness 1.3 micrometer, and this shows the measured effective dielectric constant versus frequency for two different scenario. Wg, the width of top ground plane, in one case 50 micrometer, and in second case we are increasing it to 250 micrometer, and in left figure we are considering the width of the signal line, and that is equal to the slot line is 25 micrometer, and for the right figure the values are 50 micrometer, and look at the variation. At very low frequencies, it is having higher effective dielectric constant. What that means? That means if I go back to this field plots, so we have microstrip line field as well as CPW field. Now, if we have more field confined inside epsilon r or dielectric layer, so effective dielectric constant will be higher. So, at lower frequencies, then we can say that we have less fringing field in air, but as the frequency increases, the fringing field in air, it first initially increases and then more or less it remains constant. So, at millimeter wave frequencies, you see we do not face any problem of beta variation as such, since epsilon e is more or less constant. Now, the same substrate, but we change W and S. So, in this case slot width is thicker, it is now 50 micrometer, previously it was 25 micrometer. So, because of that change in epsilon e, it is slight, previously it was almost 6.2 and now it is increased to 6.3. So, because of the increment of this increased W. Now, loss variation, again for the same substrate, silicon substrate, this is the attenuation in dB per centimeter versus frequency, measured attenuation. We are considering again Wg 50 and 250 micrometer. So, loss, what we expect, it should increase with frequency. This is the measured loss. So, it will increase, it will include everything. That means it will include the conductor loss, dielectric loss, and as well as radiation and surface wave loss. And these plots are for the CPW line, ground backed CPW line like this one, but without any periodic metallic via. So, mainly due to conductor loss, total loss increases. So, at lower frequencies, let us say at 10 gigahertz on the same substrate, this loss is typically 1.5 dB per centimeter, and it increases to 5 dB per centimeter at 100 gigahertz. So again it shows why we can't use CPW line for long distance wave propagation. We can use CPW line only for interconnects or only for chip to chip connection, right. So 3 dB loss, that means already power is half, 50% is wasted. So similarly for the right figure, we have similar variation. So the only thing is that since we are using wider W, it is now 50 micrometer, loss is little smaller compared to the previous one. So now, till now we are discussing about different types of printed lines. The most popular printed lines are microstrip and CPW line, which we already learned. There are many more like coplanar strip line and others, but coplanar strip lines usually we do not use in PCB form. It is an example of balanced line which supports only the odd mode, no even mode. So coplanar strip line, similar example is two-wire transmission line, two-wire parallel line, which we use to connect antennas for television applications or for telephone cables. But the problem mainly we face with these printed lines is higher loss. If we want to keep the loss minimum, then the only solution till now we know is the rectangular waveguide. But for rectangular waveguide we have some other problems. What are those problems? It is very bulky, and fabrication it is also very difficult, expensive. Now for some applications, let us say we need some, we want some guiding structure which won't be as lossy as these printed lines like microstrip or CPW, and at the same time we do not want the rectangular waveguide, we do not need that lower loss. Do we have any solution in between that will give some sort of compromisation in between the printed lines and a rectangular waveguide? So there is one waveguide system, and it is the planar form of rectangular waveguide. We call it synthesized rectangular waveguide in printed circuit board technology, or other terms are post wall waveguide, also it known as substrate integrated waveguide. So let me show you the pictures. So before going to that, the problem what we have seen with the printed lines is that higher conductor loss, and mainly this conductor loss it comes from the edges of the strips, both for CPW and microstrip line, and not only that, it is semi open structure. So we need packaging, and it is a problem. And if we use two parallel lines, then there will be high crosstalk between these two lines. But for rectangular waveguide we have the advantage that it is a closed structure, so there won't be crosstalk between two side by side rectangular waveguides. But the problem is its size and its volume, and also the fabrication cost. So we have a performance gap between these two, and that is where this substrate integrated waveguide or SIW comes. It performance and cost wise it is in between these printed lines and rectangular waveguide. How we design SIW? You see, this is the rectangular waveguide. We are going to obtain similar characteristics, but in printed circuit board technology. The advantage is that we can easily use that cheaper fabrication procedure used in PCB. Now, for a rectangular waveguide, it supports TE10 mode, and the synthesized waveguide what we are going to design, we are expecting that will also support TE10 mode. So, we have to obtain a similar structure in PCB technology. Now, the broad walls, top and bottom metal walls, we can easily realize in PCB form. How? Because if we buy any laminate or printed circuit boards, it comes with top and bottom metallization. So, we can utilize those metals as our broad walls of the rectangular waveguide. So, next job is to realize these side walls, PECs. But in PCB technology, how we can do it? What we do? We drill periodic vias and then metallize them. So, it becomes chain of metallic vias, and now if the separation between these two metal via is small, in that case any electromagnetic wave propagating through this channel, it can't understand this separation, and to that electromagnetic wave confined inside this channel, it behaves like a continuous sidewall. But provided the separation between these two metallic via, it should be very small compared to the wavelength of the guide. So, there are some limitations. So, now one by one we are going to see then what should be the design steps and how these steps are derived for SIW technology. Now, there are different fabrication procedure. We can drill this via by using laser beam that basically burn the substrate, and for laser beam, by changing the focus, we can actually obtain different shape of vias. So, we will see one by one what are the advantages of different shapes, how we can fabricate it. So, now this SIW, it becomes a standard form of MMIC in last 10 years, and it is being used from 1 to 100 gigahertz. Some people also used even at 140 gigahertz, and performance wise, you remember, it sits in between printed lines and rectangular waveguide. So, we start from a PCB. You can see there are several laminates here. So, we have the top and bottom metals already. Only thing is that we need to add this periodic vias. So, here we are showing some components realized in SIW technology. All of these components were designed and fabricated in IIT Kharagpur. So, this left one, this is showing one band pass filter. So, you can identify left and right side port. We are using SMA connectors and it operates till 18 gigahertz. So, it is actually not in millimeter wave frequencies, but we can design similar thing at millimeter wave frequencies. So, you can identify the vias, the side walls of this cavity, and it is showing the copper, and black color it is showing the dielectric, and we have used actually one microstrip line to cavity transition, and this inner conductor of the SMA, it is soldered to this microstrip line. So, we will discuss why we need transition. Next example, it is showing one 1:8 power divider. The input port actually it is below, it is at center, and the SMA connectors it is sitting below this substrate, and these are the output ports. And the third example is diplexing antenna. So, this antenna can radiate at two frequencies, and not only that, these two frequency signals in receiving mode, it can actually separate. The first signal it will send to port 1, and the second signal it will send to port 2. We do not need additional filter for that. And the fourth example, this is a directional coupler. So, if you feed at let us say port 1, it will basically divide the power between port 2 and port 3 with a 90-degree phase difference. Now, let us see what is the direction of electric field inside SIW. Since it is a synthesized version of rectangular waveguide in PCB form, we are expecting TE10 mode. So, you look at the electric field strength variation, it looks like a TE10 mode. We have maximum at the center point and then the minimum on the side walls as we expect for TE10 mode. So, look at the vector electric field plot on a cross sectional plane. So, we have maximum on the central plane and on the side walls again tangential electric field is 0. So, the advantages over hollow waveguide already we discussed. The fabrication procedure is inexpensive. We are using laminates to implement it. So, it is a low profile structure, almost 2 dimensional. So, if I design any components, it will be of small size and it will be really easy to integrate different components in same laminate or same PCB structure, but of course, it comes with some disadvantages. What are those? It has lower power handling capability compared to rectangular waveguide, but it is higher than the printed lines and it is having somewhat higher loss compared to rectangular waveguide, since we are decreasing the cross sectional area, but this loss is lower compared to printed lines. Next, so first let us study the losses. So, we have almost similar formula like rectangular waveguide. Now, inside we have dielectric. So, we are expecting both dielectric loss and the conductor loss. Dielectric loss again it is a function of frequency and approximately k naught square tan delta by twice kz, and the conductor loss, so similar to rectangular waveguide, it depends on frequency again and at cutoff loss will be infinity and it depends on Rm, surface resistance. So, with frequency surface resistance will increase, and we have one more additional reason. We are using periodic vias to realize the side walls. We do not have continuous side walls. So, if the separation between the side walls is more compared to lambda g, what we expect? Leakage from the side walls. So, we have one more source of loss which was absent for rectangular waveguide with continuous side walls, that is the leakage loss, and we represent it by the leakage constant alpha L. So, then together total loss alpha, this is equal to alpha L due to leakage plus alpha D, this is due to dielectric, and alpha C, this is due to conductor. And it can be shown, we have a thumb rule, frequency at which attenuation is minimum approximately can be given by this closed form expression. A effective, it represents the effective wall separation, side wall separation for SIW. Now, we have one more problem here that limits high frequency operation of SIW. We know Bragg scattering and band gap effect for any periodic structure. Now, as the side walls already we are using periodic chain of metallic via. So, we will face similar problem for this case also. So, we have to avoid then that Bragg scattering here. So, how to do that? Band gap effect we say. So, it appears for any periodic structure when beta z, this is the phase constant, multiplied by periodicity p, this is equal to n into pi, n is any integer. Let us consider the lowest order mode. We do not want any band gap effect in over our band of operation. So, we are considering the lowest order mode n equal to 1, and if I consider a rectangular waveguide, let us say the operating the cutoff frequency is 6.5 gigahertz. then the given rectangular waveguide we operate over 1.25 times Fc to 1.9 Fc. Looking at the alpha value, we have similar bandwidth definition also for SIW structure, since it's also nothing but a synthesized version of rectangular waveguide. So for a given band, then the upper cutoff frequency, it is determined by the next higher order mode, which is TE20. So for 6.5 gigahertz cutoff frequency, next the cutoff frequency for TE20 mode is 13 gigahertz. So to avoid any band gap effect over this band 6.5 gigahertz to 13 gigahertz, what we have to consider, that n equal to 1, that relationship, it should not appear below 13 gigahertz. So we are doing the same thing here. So we are considering the end of operating band k naught equal to twice kc, where kc it represents the cutoff wave number and the perpendicular direction to propagation is kx. So considering 0 leakage loss, kx equal to kc, then beta z from this relationship putting n equal to 1, this is square root of k square minus kc square. So we are just putting k naught equal to twice kc here. So it comes twice pi root 3 by lambda c. So p by lambda c equal to 1 by twice root 3. This is the limiting condition. To avoid band gap effect over this band, we have to keep the periodicity smaller than this value. We define a margin better. So to make sure that the band gap effect will not appear over the operating band, we take p by lambda c at least 0.25 or 1 by 4. So we have a limitation from here. Now let us consider the leakage loss. So we have periodic structure and the periodicity is given as p and the diameter of this via is d. Now from midpoint to midpoint separation, that is the physical dimension, is given by a. So what we are going to do, if I want to use the rectangular waveguide theorems, whatever we learn, we have to first determine what is the effective separation between these two side walls, because finally we are going to realize a continuous side walls by this periodic via. And now that effective separation between those two side walls will be what? Should we take midpoint to midpoint, or from inner edge to inner edge, or from outer edge to outer edge? There is a thumb rule for that. This A effective is different than A, and let me show the thumb rule first. So this A effective, it is usually always less than the physical dimension A. This is equal to A minus d square by 0.95 into P, and we have one more accurate formula when P by D is less than 3 and A by D is more than 5. Then you can calculate what is the effective A effective for this. So what A effective represents? Instead of periodic metal via, we are replacing it by an effective electric wall, and A effective, it represents the separation between these two electric walls. So once we have the formula for A effective, then we will be replacing the SIW by an equivalent rectangular waveguide. The thickness of that rectangular waveguide is the thickness of the substrate, and the broadside dimension of that equivalent rectangular waveguide is A effective, and inside we have epsilon r. Now okay, so we will come back to this leakage loss. Before that, let us take a 5-minute breaks. Thank you.